Section 2.3 we started last time, and we had left off on shading Venn diagrams, and I'd like to just remind you of where we were with our very last shading, this one, because it's quite similar to the next one we're going to look at. So what you'll remember that we did when we created our Venn diagrams with three sets is we made 3 overlapping circles, and then we labeled the regions of the circles. So we went straight across the top and labeled them 1, 2, 3, through the middle 4, 5, 6, the bottom was 7, and the outside was 8. And then we used our original question that we were given. I'll take off all my markings now. Here, we started inside the parentheses with the individual sets A and B, and we wrote out all the numbers that included those sets on the right-hand side. A is 1, 2, 4, 5. B was 2, 3, 5, 6, I think. And then we joined them with the symbol that was here, which was an and symbol. Let's use a different marker. An and symbol. And so that's what they have in common. That was 2 and 5. That take care of everything inside the parentheses. We moved outside the parentheses. We captured set C, wrote down everything that was in C, which is 4, 5, 6, 7. And then using this piece right here, where we had the A intersect B was 2, 5, and then this was 4, 5, 6, 7. We found the union, and union, if you remember, includes everything. It's the family picture. So we had done, the other thing happened over here is we encountered that complement symbol again. It has the bar on the top. And complement means everything not in that set. So we're going to combine both of those ideas here into our last shading example. So on this one we have the 3 sets again, like the last problem, but we also have our complements going on. So go ahead and make your 3 circles inside of your rectangle. And label them. So our set U, universal set on the outside, and then A, B, and C. And then we'll number the regions. And again, you don't have to use numbers, but your book does use them frequently. Sometimes it uses letters as well. So we'll go with those. So we're starting inside of the parentheses, and we have 2 sets. We have A and we have B complement. So I'm just going to list those, and we're going to list every number region that is included in set A. So what does set A include? 1, 2, 4, and 5. You got it. And how about B complement?
Everything except 3.
Not quite.
4, 7, 8.
Yeah, so remember B complement means all the numbers that are not in B. So the numbers that are in B include 3, like you mentioned, but it also includes 2, 5, and 6, because they're still inside circle B. Okay, so we're getting 1, 4, 7, and 8. And then we're going to combine these with the operation listed between them in the set of parentheses. What does this operation mean? And. So we need both of them to be true. It's an and statement or an intersection. So what are we looking for when we compare these lists? What they have in common. So they have the number 1 and they have the number 4. So we're going to do 1 and 4. And then our last setup here says C complement. So we're going to do C complement. Right. 1, 2, 3, and 8. And then how are we going to combine these 2 sets? That is A intersect B complement and C complement. Yes?
But they have what A and B complement and C complement have in common. So would be 1.
Yeah. So we're looking again, in this case it is another intersection. Last time we had a union at the end. This one's an intersection. So we're looking at what these lists have in common. And you're exactly right. It is the number 1. So this one would just be, whoops, we put an equal sign, the number 1. And then when we go back to our diagram, because it's asking us to do something specifically with this diagram, we're going to shade in region 1. Yes?
So how come on the last one you put all of the numbers at the end, but this one?
That happened because this is an intersection here, but over here it was a union in our last step. So you have to, it's specific to the problem. You have to use whatever symbols are going on in that particular problem. And this one that we're working on right now had intersection again at the end. So you can have any combination of those things. Okay, so we're going to look at one more application or one more don't even know exactly application, but maybe use of Venn diagrams. So the last examples that we were using were Venn diagrams, is kind of trying to shade these specific types of regions. This one actually has to do with mathematically figuring out how many numbers go in certain places. So I feel like as we look at this problem that it's a little bit like Sudoku. Okay, you're doing a little bit of problem solving with some number crunching going on. And so this example itself isn't really an application, but I'm going to show you two more problems after this that are an application using this type of process. So just want you to become familiar with this type of process first. So the first thing that I would like for you to notice here is that there are three circles that they're talking about, A, B, and C. So my Venn diagram will start the same way that it did on the last one. I've got a rectangle with three overlapping circles. And we'll label them just like before, A, B, C, and our universal set U. I don't know why I've got that on the side. I was thinking like our last ones where we had some work. So I'd like for you to take a look at the fact that the numbers that we're about to use here don't represent the same thing that they were representing in the previous problems. Before, when I was using numbers, I was using them just to sort of designate an area on the shape. One didn't mean anything specific like numerical value, right? It was just designating a location, okay? These numbers actually stand for specific elements now, right? So the N of A is 24, so maybe like the A, B, and C are college classes. A is algebra, B is biology, and C is chemistry, right? So A is saying there's 24 people taking algebra. Okay, so the numbers are actually representing elements of something here, not just locations on the picture. They also give you some information here where you have to figure things out. For example, the number of items in set A, okay, is supposed to be 24. The problem is, I'm going to have a highlighter. The problem is that means everything in the whole circle is supposed to add up to 24. There are 4 separate regions here that are supposed to all add up to 24. And guess and check would be very time consuming to try and figure out where I'm going to put these 24 so that it all adds up to 24. So it is not very helpful to start on the top line of this particular listing of data because there's too much variability going on. So if we go on to the next line of information, right, this middle one, let's just take the first one again. It says A intersect B. Okay, we talked about that before. That would be these 2 regions. Now there's not 4 items for different places. There's only 2. But again, I have the number 10, and how do I divide it up? Is it 10 and 0? Is it 5 and 5? Is it 4 and 6? I've got several options. Guess and check would be quite tedious, even with 2 options and just the number 10. So everything where it's comparing 2 sets of numbers here is not real helpful. But if you take a look at the very last one here, and whether it's the last one that's written like this is the one that's going to be most helpful for us in this particular problem. There's always going to be some piece of information where it identifies one specific location. It's not always the dead center. This one is. It has to be the intersection of A and B and C. That's the dead center of my diagram. They're not always that one. They could specifically say, depending on the language that's worded, they're telling you specifically the outside region, or they're telling you specifically it's the only C part. Right? But there's going to be something in the list of numbers where it gives you a number that is exactly in that location, and that's where you build off of. So for us, that's the 6 in the middle. So we have 6 that are in the intersection of A and B and C. Okay, does everybody understand why we're starting with 6? Okay, so as we get them sort of taken care of, I'm going to draw a line through them so that we know we've already done them, and hopefully it'll help us keep track of what's left. Now, we didn't actually talk about this one, but this N of U equals 50. That's telling you that everything inside the entire universal set is 50. So that's also that's like the worst possible place to start, right? Because you have 8 regions that have to add up to 50. So we will use all these pieces of information, just not necessarily in the order given. Now, where we are right now, and we can't use the N of U, if we go back up one step, we can actually use that middle step of information now. It said A intersect B is 10. Well, I highlighted it before, and it's this piece, and it has to be 10, right? Total 10. I've already got 6 accounted for in sort of the bottom portion of this football shape. How many would have to go in the top? 4 more. So I now have, whoops, go back, 4 here. Okay? And I've taken care of yet another piece of information. Somebody tell me what else we could do. Tell me what we might try next.
B intersects C.
B intersect C. So if you're thinking visually, I hope you're looking at it and you're talking about this region. Does everybody picture that? Wonderful. And it's supposed to equal 8. So we need 2. You're right. So we need a 2 right here. So the 6 and the 2 combined will equal our 8. Now what? Yeah, the one that's coming next after this happens to be our next choice, A intersects C. And that's our last football right here. Has to add up to 15. I already have 6 of them, so I need 9 more. And we're done with our second row of information. Now what?
A.
Sure. So we can either do the A, the B, or C. It doesn't really matter the order. We'll just go from left to right. So this circle that I originally highlighted in yellow at the very beginning, circle A, all has to add up to 24. How many does it add up to right now? 19. Right? If I add the numbers that are already in the yellow circle, they're 19. So how many more do I need so that circle A is 24? Should be 5, right? Yeah. So we've got a 5 there, and we've done that information. N of B is also 24, so that's this circle. How much is already there? 12. So how many is missing? How many are missing? Yeah, 12. And again, we're done with another piece. And then we have circle C. It's supposed to be 26. How many are already there? 17. So how many are missing? 9. And we've taken care of, okay, sorry about that. Too many pieces on my screen being moved around at the same time. That one. Sometimes people think they're finished when they get to this point. You've got a lot of numbers on there already, but you do need to remember there is still going to be a number on the outside region. It could be 0. That's a possibility. That's not an unreasonable number. It can't be negative, obviously. But it could be 0. So at this point, we're ready to use that last piece of information, that N of U equals 50. So I need you to add up all the numbers that are in all the circles. Yes?
Could we do the 24 plus 24 plus 26? Would that'd be more than 50.
It would be more than 50, and you're exactly right, whoever said because they overlap. Yeah, the 24, 24, and 26 overlap in these pieces. And that's why it's more than 50, is you're counting things twice if you try that.
Got it.
Good question. So the individual numbers themselves isolate and allow you to not count any double counts. So if we add those 7 numbers together, what do we get?
47.
It's 47, yeah. So how many are left over? 3. Okay, so that particular problem just looks like a giant, Sudoku, right? I mean, you're just trying to piece numbers in together. It has no meaning or anything like that. But we can use this to have meaning, and our last 2 examples have that. So let me show you how this works. We've got a word problem. This isn't the only way to solve these, but Venn diagrams actually work really well to solve these particular type of problems. Joe Long works on albums for musicians. Last year, he worked on 12 projects. He wrote and produced 2. He wrote 5, and he produced 7. And there's a series of questions about what he did. Now, could you reason through this without a Venn diagram? You probably could, but I'd like for us to get in the habit of thinking with the Venn diagram, because the next problem, where it's got the 3 overlapping circles, not so easy to reason through. But this one wouldn't be the worst thing in the world. We're going to do this one with a Venn diagram. So it only has 2 circles, because there's only 2 descriptive phrases that are mentioned. What are those? Write and produce. So you can actually label your circles descriptively. So like this is the projects that he wrote. So writer wrote, whatever you want to do. And this one is produced. And then we'll just label this universal set U on the outside. These are all the projects he worked on, right? So there are 3 pieces of information. I'll try to highlight them separately. It says he worked on 12. I didn't mean 3, 4. It says he wrote and produced 2. It says he wrote 5, and he produced 7. 4 pieces of information. Which piece of information is the most helpful of the ones that we're given? The write and produced. Yeah, it happens to be that same overlapping piece, much like my last example. It's a 2. And the write and produce picture here would be the trapped area between. It's a 2. Not 2 as in designating a location, but 2 as in 2 projects, right? Okay, so over here we have taken care of the wrote and produced. Now what?
Wrote a total of 5.
Wrote 5. Okay, so if he wrote 5, my circle on the left is everything he wrote. And it has to be 5 total, and there's already 2 in it, so it needs 3 more. So there's a 3 out here. And we've taken care of the fact that he wrote 5. Now what?
Produced a total of 7.
He produced 7. So the produced circle on the right-hand side has to be a total of 7, which means it's currently missing 5. So now the whole produced circle is 7. And we've taken care of the produced total of 7. So there's only one piece that's highlighted still that we haven't dealt with. It says he worked on 12. It doesn't mean we put 12 on the outside, let me just say, because that's a mistake that sometimes people will just jump to. So Emily, what did you have in mind?
You add the 3, 2, and 5,
Mhm.
which gives 10, and then you just subtract 12 from 10.
Yes. That's actually telling us that the entire universe of projects has to add up to 12. The numbers we already had added up to 10, so we need 2 more on the outside of the circles. So this is my picture. You've got yours on the same page. I don't. So I'm going to put it over here in small form. Look at that. Cool capabilities of iPads, right? And we can answer the questions. The answering of the questions is the easy part. The diagram is where you actually have to spend your time to work on it, right? So if you look at this diagram, how many projects did he write but not produce? 3. How many did he produce but not write? 5. And how many did he neither write nor produce? 2. Okay, so the questions come pretty quickly afterwards. And there's lots of other questions that could be asked. These are just a few of them about the situation. All right. Our last, I think it's our last one, is it? Almost. Very close. Our last Venn diagram one anyway. Example number 5, it's a youth group, and they're asked questions regarding songs learned as children. Upon surveying 34 youth, the following were obtained. I won't read all of them, but there's 3 different songs. Some of them say they learned a specific song, like 15 learned Jesus Loved Me. Some of them talk about learning 2 different songs, like 13 learned Jesus Loved Me and This Little Light of Mine. And the one at the bottom talks about learning all 3 songs. Okay, so a variety of different combinations of songs children had learned. So this is going to use a Venn diagram of how many circles? 3 circles. So here's my Venn diagram. And we'll draw our 3 circles. And again, like the last one, there's little reason to label them with letters. Just label them what they are. So some abbreviation of the names of the songs is a good idea. So I'll just go in order from the top down. So the first one I'll write down is Jesus Loves Me, so I'm just going to write Jesus. The next one talks about the B-I-B-L-E, so I'll label it B-I-B-L-E. And then the third one talks about This Little Light of Mine, so I'll just label it light. And we have our universal set.
Are we ever going to have more than 3?
No, 3 is going to be our max.
Perfect.
Yep. So over here, we have a lot of information. And I would make sure you also are aware that 34 youth is part of that information, even though it doesn't look like it's in this bulleted list. Right? We will need that as well. So where on this list of information is it helpful for us to start? Yep, the bottom. 13 had learned all 3. And where will that be on my diagram? In the middle. Okay. Can make it bigger, so might as well, right? All right. We took care of the one on the bottom. Now what? Yeah, we can try to work our way up. That doesn't always work on every problem, but here it seems like a reasonable next place to start. It said 14 had learned the BIBLE and this little light of mine. So that would be this piece of my diagram, right? It's supposed to be adding up to 14, so I need 1, right, to add my up to 14. And we're done with this one. I think we can move up one more time. It says 15 had learned Jesus loves me and the BIBLE. So Jesus loves me and the BIBLE would be this one. And what was that number? 2 that's missing, right? Because they have to add to 15. Okay, the last one that has one of the and statements in it is right above it as well. 13 had learned, Jesus loves me and this little light of mine. So that's this region. So what do I do now?
0.
Yeah, 0. 0 is a perfectly reasonable number to be in an area. We just haven't seen it yet. Cool. I think we can probably just keep working our way up the whole time on this one, right? 28. 28 had learned this little light of mine. So over here, this little light of mine is the bottom circle. It has to add up to 28. So how many am I currently missing?
14.
14 is it? Yes. So I need 14 in the bottom circle. The BIBLE is 19. So that's over here. How many are missing?
3.
3 are missing. Yep, for it to be 19. And the last one on our list is 15 for Jesus loves me. So it's another 0. Yeah. Okay, good so far? Okay, what piece of information have I not used? Yep, the universal set. And that talked about the 34 youth. So my 34 youth, how many youth are already present in somewhere on this graph? 33. So I'm missing just 1, so 1 will go out here. And with that diagram, we'll make it smaller over here. We can answer our questions. So these questions are posed a little bit differently because I wanted you to see some of the other types of questions you could be asked. A says, how many learned exactly one of the songs? So can you tell me what numbers would that be in our picture?
3 and
The
14.
14 plus the 3.
Okay, the 14 plus the 3. So specifically, we should be looking in these outer circles that don't have the overlapping pieces, right? So as you're doing these problems, if you mess up the diagram, I mean, that happens, but it's automatically going to mess up your numbers, right? I mean, it just is. So if I were grading this on a test or if the homework is being graded by the grader or whatever, what they're going to look for is that your numbers match your diagram. So it will help them a lot if you actually write down the numbers that you think you're adding together to get this mysterious number 17, if that's not really the right number. You know what I mean? So they can say, oh yeah, they added the right numbers from their diagram together. 0, 14, and 3 were the right numbers. So even if your numbers are wrong, your question answers are correct. How about at least 2 of these songs? What picture parts would those be? What numbers?
0, 2, 1, 3.
That's part of it. 0, 2, and 1.
Oh, this is in this, so 13.
And the middle 13, yeah. So this phrase, at least 2, means 2 or more. So we get the 13 as well. And so how many does that end up being? Yeah, 16. So we have 17, we have 16. How about none of these songs? 1. And this little light of mine only? 14. Okay, so some problems you're adding up pieces of the diagram together, and other parts of it you're just isolating a specific location. Okay, so that's it for Venn diagrams. I got one more example for us in this section before we're done. And it's talking about the Cartesian product. So let me remind you what the Cartesian product was, since that came about last time. This is the Cartesian product. The Cartesian product was pairing things up, where the pairs had to be from group A and group B. And you could only pair things from group A with things from group B and so forth, and you're finding all the pairings. Okay, so we did this sort of ordered pair kind of look at things. And the question that we're asked in the last question, is the Cartesian product, is the Cartesian product commutative? Why or why not? So if you remember, commutative means you can change orders around, right? So, for example, addition is commutative. 3 plus 5 is 5 plus 3, right? That's commutative. So is the Cartesian product commutative? Can you change its order around?
Yes. Is that like the dating thing where you pair one up?
Kind of, yeah. So let me show you, well, we can use our one over here actually, would be fine. You have this one over here, and we can talk about it from here. I'll use this one and put it over here. Okay, so this is our reference point. So in order to be able to have commutative property, it means a specific element has to be the same if you reverse it. Okay? So when I was talking about an example with our numbers, right? 5 plus 3 is equal to 3 plus 5. That works because I took an individual pair of numbers, I switched the order, and it was exactly the same. So the question is whether or not you can do that with a Cartesian product. So in other words, can I take x1 and switch the order and make it 1x and make them equal? That's the question this is asking. We'd be switching everything, so this would actually say B cross A. So the question is, would we have the same grouping of elements if I switched all the letters and numbers around like that?
Yeah.
So I want to give you an example to consider where you're going to see very quickly that you can't, because I know you're all tempted to say yes, because many of you are saying yes to me. Consider the ordered pair, i.e. point, 1, 3. Does this equal the point 3, 1? It doesn't. So a counter example, remember when you're trying to decide if something works all the time, you have to think about it in its different, sort of facets, I suppose. And so when we think about grouping these numbers together, if I switch everything, right, if I had a collection of points in our xy plane, like 3, 1 and 1, 3, and I switched all the numbers around, I would end up in a different location, right? Yeah, so the Cartesian product is actually not commutative. So the answer here is no, and the reason why, at least one of the justifications, right, counterexamples, is the one that I just gave. The ordered pair 1, 3 is not the same as the ordered pair 3, 1. It's still a pair of points. I've still grouped 1 and 3 together in a pairing, but now they have locational position, which causes a problem with us saying that we can switch them and it actually means the same thing. Does that make sense? Yeah, it's a little bit of a tricky one. Okay, so 2.3 is finished. We're going to get into groups. You've got 4 group work problems, and take a look at those today.